Howdy, today I'm going to be presenting my research that I've been working on so far for the Undergraduate Research Scholars Program. My name is Victoria Rivera and I am a senior computer science major. The topic of my research is analysis of calling context encoding algorithms, and my faculty advisor is Dr. Kim. So starting off, we're going to talk about some simple components of computer programs that relate to my research. So computer programs have many different parts, and a key element of programs is that you typically don't run or execute instructions from top to bottom. You start off in the main function. So in this example that I have here, the main function is this bottom function actually called int main, and it has one line of instruction, this foo parentheses and colon. This is essentially a function call. And functions are very important for my topic of research. And what a function is it's a specific section of code that can be called at any point, and it is written to perform a certain task. It can be called many times throughout the program, and functions themselves can call other functions. So in this example that you see here, this main function actually calls the foo function. So foo is this function actually written before main. And so once we are at foo, we can see that the only line within the foo function is calling another function called print. So print will then, or your program will then go up here to the print function and perform whatever line of code that is inside these curly braces. So here, the only line is to print out hello world. And then once a function is done executing, once you reach the last line of code, that function will go back to the function that it was called by. So print is going to be done after printing hello world, and then the program itself will return back to the foo function and see that there's no other lines of code that need to be executed, so that it will go back to the main function, and then the main function will continue on doing its thing. Now that we understand what functions are, we can talk about calling context and its encoding. So there is this thing called a call stack, which holds information of the currently running functions of your program. So from our example, when int main calls foo, main goes in the bottom of the call stack, and then foo goes on top of it. And when foo calls print, print will go on top of foo inside the call stack. And you can imagine in a more complex program, then this call stack can get increasingly very large and expensive to keep track of. So that's why we want to monitor our program's call stack efficiently through calling context encoding. And calling context is essentially all the functions that have been called currently through your program's execution. There are several existing encoding schemes already out there, such as precise calling context encoding, CCT-lib, and valence. For the purpose of this research, the main ones that I'll be talking about are precise calling context encoding and CCT-lib. So PCCE is a static instrumentation calling context encoding scheme. What I mean by that is that it updates your target program's binary file before it starts executing or before the program is running. And this binary file is actually machine code that is understandable only to your computer. And so it will update this before you run your program. And it keeps track of this calling context using your CCID, and it updates at each function call. And it uses graph theory to generate a graph that has nodes that represent functions. And these edges that connect the nodes are encoded with an edge weight. And PCCE does require a decoding algorithm. Now, CCT-lib varies from PCCE because it is a dynamic instrumentation tool. So it actually updates your target program's binary during runtime. That's what dynamic instrumentation means. It monitors for these pin trace entries. And once you have a pin trace, it will go through its encoding scheme and update its value based on wherever you are in your program. And valence, again, is just a variable length calling context encoding scheme. It varies from PCCE and CCT-lib in that it actually encodes your calling context in a list value, not an integer. Now I'm going to introduce distinguished calling context encoding, or DCCE. DCCE addresses some limitations of precise calling context encoding scheme that we had talked about previously. It does this by distinguishing between calling contexts of different ending nodes in a path. So the way that it does this is that given a CCID, it can tell the difference between calling context path if you have a different ending node. So as you can see from this example graph on the right, main calls phi and main calls foo. So each node represents a function and each edge represents a function call within your program. So these two call paths have the same CCID, but DCCE is able to tell the difference between these two call paths, even if your ID is not unique. And so again, it encloses your calling context into an encoded integer CCID. And these edge weights that you see on the graph are actually stored within a CC file that is taken as input for DCCE. And DCCE does not require any overhead, unlike PCCE for decoding. Again, it instruments the target binary before and after each function call, and it updates your CCID based on the edge weight in your .cc input file. It does the updating by adding the encoded edge before the function call and then subtracting the encoded edge after the function call through binary instrumentation. This slide contains the main components of DCCE using our simple example that we've been talking about. So we have our source code on the left. In the middle, we have the call graph that pertains to our source code, and we have the corresponding .cc file with the encoded edge weight information to the right. As we can see, here in the main function, we have two function calls, foo and phi. Before and after each function call, the CCID will be updated based on the corresponding encoded edge weight from the graph. And we find this in the .cc file. So as we can see, the connection between main and foo, that encoded edge weight is 0. So before and after each foo function call, that CCID will be updated with 0, and then after the function call, it will be subtracted by 0. And this is essentially what binary instrumentation is going to be doing. We are creating a DCC pin tool version because we want to show the efficiency within DCCE against other encoding schemes. Ultimately, we want to replace the CCT lib scheme in other analysis programs such as RedSpy and DeadSpy to show how DCCE is an improved encoding scheme to the ones that are currently existing. And we're going to do this through efficiency in runtime. And the way that DCCE pin tool is implemented is, first, we want to take the .cc information in that file and input it into a nested map data structure. And this data structure is just essentially like a dictionary where we can easily access information without having to look through the entire file. And at every instruction within our target binary, we want to look for a certain call function. Once we have a call function, we want to make sure it is within our .cc file or the nested map data structure. If everything aligns, we want to get the memory address information of our caller and callee function. And using that, we will pass that as parameters into our callback functions that will actually be doing the updating of our global variable CCID. So this is just the overall DCC pin tool flow, and it kind of gives you a visual of everything that I've been talking about so far. So our target application will be inputted into the DCC pin tool after it's gone through the call graph generator and generated the .cg file, which contains caller, callee, and call site information. Once that's complete, then we enter the DCCE space. The CG file will enter the calling context encoder, which is when we actually get the encoded edge weight IDs or the encoded edge weights for each function to call. And then that is the .cc file that we will parse and we will use within our DCCE pin tool to monitor the calling context as our target application is executing. Once we've finished implementing DCCE, we want to replace CCTlib with our pin tool version within the RedSpy and DeadSpy applications. And we want to see improved efficiency and execution time within meaningful data and graphs, because we want to show that our novel idea of DCCE is an improved encoding scheme from what is already existing.